Chapter 7.6 deals with potential energy. So we're going to talk about two main ways to classify potential energy. We're going to look at gravity and springs. So if we want to talk about gravity, first thing we need to do is consider an object with the potential to fall, right? So you can imagine something sitting on the edge of a chest or something. And if left there, it falls off, right? So the question that you may ask is, if I have this object here at some height, and it starts with a 0 initial velocity, is how much kinetic energy does it have when it hits the ground? Well, we can figure that out, right? We know that the work is equal to the change in kinetic energy. And we can look at the work done by gravity on this block. During this free fall, the only force acting on it is gravity, so that's the only force doing work. So let's look at the work done by gravity. And that's going to be the force of gravity times the height. And let's look, our motion is in the same direction as the force. So we have cosine 0, which is 1. So it's just the force of gravity times the height, which will be equal to mg times h. So that's the work done on an object falling in free fall. And that's equal to the change in energy, right? So where does that energy come from, right? We introduced this idea of a system that includes the Earth and the object. So in this system, the gravitational force is not an external force. It's an internal force to the system. So it doesn't change the total energy of the system. And we describe the position here as having some potential energy, right? It has the potential to create kinetic energy. And we just calculated what that is equal to. That's the work done by gravity, right? So the gravitational potential energy of an object is equal to mgh for whatever height it is above your 0 point. Okay, and this again, we're using little g here. So this is our near Earth approximation for the gravitational field strength. If we want to look at it in more general terms, we haven't talked about Newton's law of universal gravitation in a while, but the force of gravity is G m1 m2 over r squared. And you could talk about the work done here as well. I'm not going to go into detail right now. Maybe when we revisit gravity, we'll do that in detail. But I just wanted to go ahead and mention that it's not going to be the same when you talk about, large distances rather than just near the surface of the Earth. All right. So the other thing I said we were going to talk about was springs. So we're going to calculate the work done on a spring, just like we calculated the work done by gravity. So if I have a spring that's compressed or stretched, right? And we release some block, then if the spring pushes the block to make it move, then that's some type of energy transfer. And in this case, we're going to consider the spring as part of the system. The compressed or stretched spring has some potential energy associated to it. So we have a potential energy in the position of the spring. We've calculated this before. The work done by the spring force between an initial and final X is one half K X final squared minus 1/2 K X initial squared. So if we talk about this in terms of the energy, remember for the gravitational situation, we said that this is relative to a chosen 0 point. I said it, I didn't write it, now we've written it. Well, we have a natural 0 point for this situation, right? If our X naught is defined to be the equilibrium for the spring, and we know that this term is going to go to 0, and we're left that the work done taking a spring out of its equilibrium position is given by 1/2 kx squared. And if we release the spring is going to do that same amount of work. So this is the energy stored in the spring. So if we do work lifting an object, we're storing energy in that height, because even if there's no kinetic energy there, it is going to move when you release it, because it's going to be drawn back to the Earth. In this arrangement of the Earth object system, there's a potential. When we stretch or compress a spring from its equilibrium position, we have a potential because it wants to return to its equilibrium position. And if that spring is attached to something or pushing on something, then it'll transfer some of that energy. So to sum up, we have gravitational potential energy is mgh near Earth. Right, that's our uniform field approximation. And the spring potential energy is 1/2 kx squared, where x is the displacement from the equilibrium position. We're going to talk more about how we classify the forces involved and how that relates to using a potential energy in another section.